So before we get into too much math stuff, I think that uh, our next midterm, I believe that I have it scheduled for next Thursday. So that is not next class, but the class after that. Um, the exam will be a take-home test. Obviously, I cannot prevent you from using any sort of technology, so I'm not even going to try. I can't prevent you from using your notes, so I'm not even going to try. The one thing I am going to request from everybody is that you do not ask for help from any people. So that means no working together, and that also means no reaching out to tutors or math lab people or anything like that. Of course, you can always ask me if you have any questions, and I'd be happy to answer them. I will give you the exams on next Thursday, and then I will collect them sort of. I'll put up a Dropbox or a assignment on D2L, and I'll have you guys submit those by Tuesday. So if anybody has any questions about that experience, feel free to ask me. It should be pretty straightforward. The test is going to be a little bit different than it would normally, but I don't think it'll change that much for this class. It might be a tiny bit longer or harder, but it won't be significantly longer or harder. Just try to be as honest as possible with that. Does anybody have any questions before we get into our math topic for today?
It's still gonna be the 12 questions, pick 10, right?
Probably, yeah. Yeah, for this class, it'll probably be 12 questions, pick 10. So that shouldn't change. And to turn it in, I'm okay if you guys have like a printer and you can print it out and fill out the test and then take pictures of it or scan it. That would be ideal. If not, if you can clearly label on separate sheets of paper like which question is. So like on one sheet of paper, do question number one. On one sheet of paper, do question number two, and upload those pictures. That would be fine. If you feel comfortable using some sort of typing, like a any sort of typing interface to do these types of problems, you can do that as well. I will. I'm going to be pretty flexible about how I'll collect this. Okay, with that out of the way, so this class we're going to be talking about solving exponential and logarithmic equations. Next class we're going to be talking about using exponential and logarithmic functions to model the real world, so real world applications. And then on Thursday itself we will actually still have class. I want to use that hour to do a review session really quickly. So I will go through the topics as usual, and if you guys have any problems that you would really like to see, I can pull those up. Otherwise, I can get you guys a review sheet, or we can work through a review sheet. So hopefully that will be effective and useful. Other than that, let's go ahead and hop into it. So um, for solving exponential equations, there's a few different types of situations you can find yourselves in. Um, One of the most important things that's the most useful to us when we're solving exponential equations is that if we have, so there's an equivalence property of exponents, and it says that if b to the power of x is equal to b to the power of y, then x is equal to y, right? If you have two exponents that have the same base, then the exponents themselves must be the same as well. Okay. So if kind of very quickly, if 2 to the power of x is equal to 2 to the power of 4, that means that x has to be equal to 4. Right? So one of the ways in which you could solve exponential expressions that all have a common base is you could collect everything on each side and then set the exponents equal to each other. Right? Usually it's not going to be quite as straightforward as that first example there, 2 to the power of x equals 2 to the power of 4. That seems like a little bit of low-hanging fruit. But a good example of the type of problem that you can expect to see is 2 to the power of x plus 5 is equal to 8 to the power of x plus 1. So notice immediately that these don't actually start with a common base. However, 8 is equal to 2 cubed. So we can rewrite this as 2 to the power of x plus 5 is equal to 2 cubed to the power of x plus 1. And if we go back to our exponential properties, we had a property for when we had a power to a power like this. And that property said that we could then multiply the exponents. So this is 2 to the power of x plus 5 is equal to 2 to the power of 3 times x plus 1. And now we can apply our equivalence property. So that tells us that x plus 5 is equal to 3 times x plus 1. Note, this is equivalent to applying log base 2 to both sides. Log base 2 of 2 to the x plus 5 is equal to x plus 5 times log base 2 of 2. This is our power property of exponents. And then log base 2 of 2, well, what power do we have to raise 2 to get 2? That's way too many 2's. But it's just 1, right? So this is just x plus 5. And the same goes for the other side as well. But now that we're here, we've gotten rid of the exponential parts. It's just a matter of solving for x, and this is linear at this point, right? We have x plus 5 is equal to 3x plus 3. We can subtract 3 from both sides, and we can add x, or subtract x from both sides. And we get that 2 is equal to 2x, so x is equal to 1. For exponential equations, that really is it. You don't need to check your answer unless you want to check your answer because you like to make sure that you're correct. But you get your answer and you're good to go. These can be a little bit tricky. Frequently, they might not look like they have the same base, but you should always check to see if you can write your exponents with a common base, right? So, for example, 2 and 1 over 4 have a common base because 2 is equal to 2 to the power of 1 and 1 over 4 is equal to 2 to the power of negative 2. 1 over 4 is 1 over 2 squared. 1 over 2 squared is 2 to the power of negative 2. So before you dive straight into a problem like this, always check to see if you can find a common base for the exponential terms. Okay. We're going to see why you really, 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 really want to check to make sure if you can find a common base for your exponential terms in just a minute here. Any questions about this first example? All right. So Sometimes you won't have a common base. If no common base can be found, then you need to apply a logarithm. So for example, if we have 3 to the power of x minus 4 is equal to 300. I don't think that there's a way to write 3 as a power of, or to write 300 as a power of 3. And in fact, solving this problem is literally finding what that is. So in order to solve this, we're going to need to actually go in and apply logarithms and pull out our answer that way. So what I mean by that is that you can use logarithms to get exponents out of exponential functions, right? So whenever you have the x in an exponent, you need to use a logarithm to get it out, unless you can apply that equivalence property, which is secretly using a logarithm. So because we have 3 to the power of x minus 4, the logical base, so it seems useful to use log base 3. Generally, if you have exponential equations and you don't have a common base, you should pick one of the bases that exists there to use with your logarithm. When you only have one exponential part, then it seems you should use the base for the part that actually has an exponent. Okay. So here, 3 to the power of x minus 4 is equal to 300. Then if we apply log base 3 to both sides, on the left-hand side, this simplifies. Log base b of b to the power of x is just x, right? In some sense, the logarithm and the exponential part cancel. You can also use the power property and then cancel if you prefer. But we get that x minus 4 is equal to log base 3 of 300. And then it's just a matter of adding 4 to both sides. X is equal to log base 3 of 300 plus 4. The one caveat here is that if you do not have a calculator that's capable of evaluating log base 3 of 300, then you need to rewrite this using the change of base formula. So recall log base b of x is equal to log b, or log x over log b, or ln of x over ln of b. So if we want to, we can rewrite this as ln of 300 divided by ln of 3 plus 4. And we can use our calculator to figure that out. So if we do ln of 3 and, or sorry, ln of 300 divided by ln of 3 plus 4. So that's approximately 9.192. For your answers for this, I'm pretty okay with you just rounding to do 3 decimal places, where it seems reasonable. If I need you to round further than 3 decimal places, then I will be very explicit about that. But generally, it's best practice to both provide an exact answer, this ln of 300 divided by ln of 3 plus 4, and a decimal approximation, 9.192. There are certainly situations in which you may need to collect some exponents, and there are some situations where you may need to apply some things to some quadratic forms and things like that. So some things can change around a little bit. For example, one final type that you may see is something along the lines of, so for quadratic, if we had something like e to the 2x minus e to the x is equal to, or e to the e to e to the 2x minus e to the x minus 6 is equal to 0. This kind of looks like a quadratic, right? So if you think way back to the very beginning of the year when we talked about solving using quadratic techniques, we saw some things that may have looked like x to the 4th minus x squared minus 6 is equal to 0. And we could do a substitution, u equals x squared. And we get x squared minus x minus 6 is equal to 0. Or, sorry, u squared minus u minus 6 is equal to 0. The same idea is true here. We can use a substitution. And here our substitution will be u is equal to e to the x. Then u squared is equal to e to the x quantity squared, which is just e to the 2x. So we get that u squared minus u minus 6 is equal to 0. And we can factor this. U minus 3 times u plus 2 is equal to 0, which means that either u is equal to 3 or u is equal to negative 2. But u is just e to the x, so e to the x is equal to 3 or e to the x is equal to negative 2. Notice that this does not always mean that you have two solutions. If e to the x is equal to 3, then x is equal to ln of 3, right? So this one does have a solution. But e to the x is never less than or equal to 0. It just never happens. Exponential functions are always positive. No matter what power I raise a positive number to, it will always remain to be a positive number. So this has no solutions. So this side of it does not yield a solution. Our only solution is x is equal to the natural log of 3. And if we want to quickly just get a decimal approximation for that, the natural log of 3 is approximately 1.099. The last form of exponential equations we'll see is going to be one that where we cannot find a common base, and we're going to need to sort of snake our way through the entire problem. These are by far the most involved algebraically things that we'll do in this unit. Okay. So if you do not have a common base, apply a logarithm and then but it'll get messy. So for example, 2 to the x plus 1 is equal to 3 to the x minus 1. we do not have a common base. 2 cannot be written as a power of 3, and 3 cannot be written as a power of 2, at least sort of naturally. We can, of course, write any number as a power of another number using logarithms, but that's a mess, right? And that's what we're trying to figure out anyways. So instead of trying to find some magical way that we can shoehorn in the equivalence property, we're just going to use the idea underlying the equivalence property and apply a logarithm to both sides. So let's apply log base 2 to both sides. As a note, you can just apply a natural log to both sides if you prefer. The math gets a little messier when you use a natural logarithm on both sides. You can also apply log base 3 to both sides. The math is almost the same if you apply log base 3 to both sides. I just chose 2 because it was the first number I saw. So that was actually in the equation. So if we apply log base 2 to both sides, we get log base 2 of 2 to the x plus 1 is equal to log base 2 of 3 to the x minus 1. On the left-hand side, the log base 2 and 2 to the power of x just cancel, and we get x plus 1. On the right-hand side, we can use the power property of exponents to get x minus 1 times log base 2 of 3. Log base 2 of 3 is a number. It's a constant, right? It's something that we could solve for. It's ln of 3 divided by ln of 2. And it's like 1.585. However, I do not want to simplify it until the end. I just don't want to hang on to a weird decimal. If you feel more comfortable with the weird decimal instead of the log base 2 of 3, that's totally fine. So at this point, what we need to do, since we have 2 different copies of x, we need to collect all the x terms onto one side and collect all the non-x terms onto the other side. So that means distributing this log base 2. So x plus 1 is equal to x times log base 2 of 3 minus log base 2 of 3. And then I'm going to subtract x log 2 of 3 from both sides. And I'm also going to subtract 1 from both sides. So we get x minus x log base 2 of 3 is equal to negative 1 minus log base 2 of 3. And then we can factor out on both sides on the left hand side, sorry, we can factor out an x. So we get x times 1 minus log base 2 of 3 is equal to negative 1 minus log base 2 of 3. And then we can divide both sides by 1 minus log base 2 of 3 to get that x is equal to negative 1 minus log base 2 of 3 over 1 minus log base 2 of 3. Of course, if your calculator doesn't take natural logarithms, or if your calculator doesn't take arbitrary base logarithms, then you will still need to use a change of base to evaluate this. This is an exact form of an answer. Your exact forms will vary depending on which logarithm you applied. It's possible that if you applied log base 3 of 2 or log base 3 to everything instead, you would get a different looking answer. when you evaluate them to their decimal approximation, you should always get the same decimal approximation. If you had solved this using a natural logarithm or a log base 10 instead, you would also get a different looking answer, but it's going to be equivalent in the end. So here we're going to apply the change of base formula. So we get -1 minus log 3 over log 2 divided by 1 minus log 3 over log 2. And we're going to go ahead and plug that into our calculator. So that's -1 minus that. Oops. Divided by 1 minus ln3 ln2. So we get our answer as approximately 4.419. So this trick here, where we collected all of our x terms on one side and collected all of our non-x terms on the other side, then factored out the x and divided by the stuff that wasn't the x, is something that actually is a really common algebraic trick that trips people up a lot. So being aware of it and having seen it is going to be really, really helpful. And it's going to be something that is there will be questions like this on the test that you need to use this specific type of property on. And if you do not spot a common logarithm, like a common base for your logarithm, this is the path you end up going down. So you want to be a little careful, right? In particular, if we go back to our very first example, the 2 to the power of x plus 5 is equal to 8 to the power of x plus 1. If we hadn't spotted that they were a common base, we would end up with 2 to the power, or we would take a log base 2 of both sides, and we would get that log base 2 of x plus 5. We would end up with x plus 5 is equal to log 2 of 8 to the x plus 1. And then x plus 5 is equal to x plus 1 times log base 2 of 8, and you would keep going from there. This does get a little bit simpler if you manage to spot and realize at this point that log base 2 of 8 is 3. But these, like the fact that log base 2 of 8 is equal to 3 is exactly equivalent to the fact that 8 to the is equal to 2 to the power of 3, right? Or maybe I should write it as 2 to the power of 3 is equal to 8. This is literally the definition of a logarithm. So, this covers more or less all of the situations that you'll see an exponential function that needs solving in. Of these situations, it's probably most common to see ones that look like this second example here, that 3 to the x minus 4 equals 300. That's the most common situation that you apply these in, but it's definitely useful to know how to deal with all of them. Any questions about solving exponential equations before we move into the other half of solving equations? All right. So let's talk about solving logarithmic equations. So once again, we have a couple of different situations. We either have all logarithmic terms, or not all log terms. One thing that we will not do, because it is a non-trivial problem, is how to deal with logarithms with mixed bases. If you have logarithms with mixed bases, you would need to then rewrite them to have the same base using the change of base formula, and that introduces a lot of messiness into it. So you want to be really careful if you run into that situation. We're primarily going to focus on logarithms that have the same base. Okay. So let's deal with this all log terms first. If all terms in your equation are logarithmic, that is log base b of something, then we can apply then we can condense, then apply the equivalence property for logarithms. And the equivalence property for logarithms is predictably very similar to the one for exponents. The equivalence property for logarithms is if log base b of x is equal to log base b of y, then without fail, x must be equal to y. This is equivalent to applying b to the power of both sides. In other words, if we take log base b of x is equal to log base b of y, we just do b to the power of b to the power of, and then sort of the b and the log base b cancel, and we get x is equal to y. So the equivalence property of logarithms, it frequently applies, but we're frequently going to have to use those log properties that we talked about last class to expand or condense logarithms before we can use this equivalence property. So for example, let's say that we had ln of x minus 2 plus ln of x minus 3 is equal to ln of 2x. Well, everything is a logarithmic term. We have three terms, ln of x minus 2, ln of x minus 3, and ln of 2x. And all three of those terms are ln of something, so they all have the same base. So we want to apply this logarithmic equivalence property, but first we should condense. On the left-hand side, we have ln of x minus 2 plus ln of x minus 3. So we can rewrite that as ln of x minus 2 times x minus 3. Right? That addition on the outside turns into multiplication on the inside. And then we could apply our equivalence property. We have ln of some stuff is equal to ln of some stuff, so the stuff inside must be equal. X minus 2 and x minus 3, or times x minus 3 is equal to 2x. And at this point, we're just solving. We've got something that looks like it's going to end up being quadratic, and we're going to go from there. X minus 2 times x minus 3 is x squared minus 2x minus 3x minus 6, or plus 6. So that's x squared minus 5x plus 6 equals 2x. So x squared minus 7x plus 6 equals 0. And this factors, right? It factors as x minus 6, x minus 1 is equal to 0. So x is equal to 6, or x is equal to 1. But be careful here. You must check solutions for log equations. Come on. Logarithmic equations, much like radical equations, can have extraneous solutions. Okay, not all solutions always work. If we go back to our original equation and we plug in x is equal to 6, then we get ln of 6 minus 2 plus ln of 6 minus 3 is equal to ln of 6. And that's, ln of 12. And that's true. That's ln of 4 plus ln of 3 is equal to ln of 12. And, if you want to plug that into a calculator, you can. Ln 3 plus ln 4 is 2.485, and ln 12 is also 2.485, right? So that one checks out. But when we plug in x is equal to 1, we have an issue. We get ln of 1 minus 2 plus ln of 1 minus 3 is equal to ln of 2 times negative 1. And that's ln of negative 1 plus ln of negative 2 is equal to ln of negative 2. That can't be true. You cannot take a logarithm of a negative or 0. It's not possible. It doesn't work. So x equals 6 is a solution. X equals 1 is not a solution. Oh, this was ln of 2, not negative 1 here. Sorry. The only solution to this expression is 6. Even though we ended up with a quadratic that when we solved it, we should have had 2 solutions, one of them was extraneous. It failed to work. Okay? So our answer is only x equals 6 and not x equals 1. You have to check the answers for your logarithmic equations. Even if both solutions, or if you get multiple solutions and they both manage to work, you need to at least show me that you've checked, okay? So go ahead and at least, plug those in, show me that it works, make sure that you made some token effort in order to check to see that it works. If you don't, then I'm going to assume that if you don't show me that you did, then I'm going to assume that you didn't, okay? It is not always true that you will have an extraneous solution. Sometimes both solutions do actually work. It is also not always true that you have any solutions. You may have 2 extraneous solutions and there's no solution to the equation. That can also happen. So always check your answers on logarithmic equations. Any questions about this example before we move on to our last sort of different unique case? All right. So the last situation is when we have log expressions and non-log expressions, or not log terms and non-log terms. In this situation, you have a couple of different ways of thinking about it, but you're always going to collect all your logarithm stuff on one side and all your non-logarithm stuff on the other side. Okay, and then once you have that, hold on. I just realized I made a typo in the example I was going to do. Yeah, okay. Once you have, so collect all log terms and then condense them. Then collect non-log terms on the other side. Then you can do one of two things. First is use the definition of the logarithm to rewrite as an exponential equation. That is, log base b of x is equal to y is equivalent to b to the power of is equal to x. Or two, you can raise both sides to the power of b. That is, if you have log base b of x is equal to y, we can do b to the power of both sides. And in that case, your logarithm and your b to the power will cancel on the left, and you'll just end up with b to the power of y on the right. You'll still end up with the same form either way. This is just two ways of doing the same thing. Okay. So for example, let's go ahead and solve log base 2 of x plus log base 2 of x minus 1 is equal to 1. So to begin with here, we already have all of our log terms on the left-hand side and all of our non-log terms on the right-hand side. That's not always going to be the case, but it is handy when it happens. Okay. So we need to combine and condense our logarithmic terms on the left here. Right. So we have addition between the two, so that gives us log base 2 of x times x minus 1 is equal to 1. Or if we prefer, log base 2 of x squared minus x is equal to 1. And then we can either do 2 to the power of both sides here, or we can rewrite it as a logarithm, as an exponential expression. Either way, we're going to end up with x squared minus x is equal to 2 to the power of 1. And of course, 2 to the power of 1 is just 2. And this is a quadratic. We know how to solve quadratics. We're going to pull the 2 over to the left-hand side. X squared minus x minus 2 is equal to 0. And factor. We get x minus 2. X plus 1 is equal to 0. So either x is equal to 2 or x is equal to 1, or negative 1. Let's check our solutions. X equals 2 works out just fine. Log of 2 plus log of 2 minus 1 is equal to log of 2 plus, log base 2 of 2, log base 2 of 2, log base 2 of 2. So log base 2 of 2 is 1, and log base 2 of 1 is 0, so it is 1. So this one works. Log base 2 of negative 1, and we already have trouble, right? Log base 2 of negative 1 minus 1 is equal to, doesn't exist, right? Can't take the logarithm of a negative number. So x equals negative 1 fails. So the only solution is x equals 2. And that is more or less exponential and logarithmics, solving exponential and logarithmic equations. Most of what you'll see is going to be one of those sort of similar to one of those 5 cases. There may be some different numbers. This stuff is all very, there are some types of these problems that you can do without a calculator, but most of them are going to require you to use a calculator. So make sure that you're, being diligent and giving good decimal answers. Okay? Does anybody have any questions about any of the examples we just went over? Okay. So what I want to do at this point is I think we will end the lecture there. I'm not going to pile more information on top of you right now. Next class, we'll look at sort of applying these in applications and using them in real world situations where you can use exponential functions to model things. We already talked a little bit about doing it with compound interest, but it turns out that there's a lot more phenomenons in life that are that grow in an exponential pattern. So that will be next class. I will go ahead and post up a set of problems for you guys to work on for the next hour, and I'll be kicking around in one of the voice channels for you guys to ask questions about that. And also, I will actually post a homework assignment. I think I forgot to last time, so I will post one that covers the rest of this unit. That'll be due. I think I'll probably have the homework assignment due on the day that I hand out the test, so that you're not trying to do the homework and the test at the same time. So. Any questions before I let you go? Does anybody have anything they want to ask or say or anything like that? Okay, guys. I will post some stuff, and we will come back around again on Tuesday. All right.